Alright, in this video today, we're going to show you how to design or size a timber beam, including the beam stability factor. And we're going to use the special Dr. Rachel Mosier method.
Step 1.
Write the problem. Duh. Now this is crucial, doing the Dr. Rachel Mosier way. If you don't write the problem down, you will get points taken off. So let's look at the problem statement. We're going to design a Hemfer number 1 with the 12-foot simple span floor beam. It's going to support a point load at mid-span of a dead load of 500 pounds and a live load of 1,000 pounds. Assume the point load braces the beam. So you can see our drawing that we have here. We've drawn the simple span beam with our point load, PU, at mid-span, and that dimension is denoted as LU. So the next part, you're going to write down your givens. These were given in the problem statement. We have a Hemfer number 1 species of wood, a 12-foot simple span, and our dead load of 500, and a live load of 1,000 pounds. Now we're going to have to assume that the design factors, CT, which is your temperature, CM, moisture, CI, your incision factor, and CFU, your flat use factor, that they are all equal to 1.
Step 2.
Find the load combinations. So here you can see that we have PU equal to, wait, what are these equations? Where did we get them?
Table 6.2.
Awesome. So on the left you can see our load combination equations. And this again is from table 6.2. And using the Dr. Rachel Mosier method, you need to reference where you get your information from. So we have our dead load and our live load, which was given to us earlier in the problem statement. So using the equations from, again, table 6.2, we're just going to plug and chug accordingly. So next, we're going to find the highest value of PU. So looking at the equations that we've solved, it looks like equation 2 gives us the highest value of 2,200 pounds. So we're going to go to equation 2 on table 6.2, and we find that lambda, which is also our time effect factor, is equal to 0.8. And this is typical for occupancy.
Step 3.
Find the moment. And this is by far the easiest step out of all of them. So we're going to look again at our drawing that we drew from the design statement. So we have a simple span beam, which means we have 2 pins located on either end. And we only have one load, which is located at midspan. So, using table 8.3 in your textbook, the moment equation is given to us for this exact type of problem. Mu equals Pu times L divided by 4. So going back to step 2, we found Pu, which is 2,200 pounds. And our L is given to us in the problem, 12 feet. So again, we're going to plug and chug. So here we get 6,600 pounds per feet. But in this problem, we'll need pounds per inches in order to solve for dimensional lumber. So make sure that you convert, giving us 79,200 pounds per inch.
Step 4.
Find design values. So, in this step, we're trying to solve for F star B. So we have the equation written down. We need to have FB phi, our lambda, and earlier we did assume that the design values CT, CM, CI, and CFU equal 1. So now we just need to find our KF factor. And this was found on table 6.3 in your textbook. Our phi was found in table 6.4, and our value for FB, which is our bending stress, was in table B.2. Now we're also going to use the lambda, our time effect factor that we found earlier of 0.8, and we're going to plug it into the equation. So here we have our neat and handy Excel sheet table, and we just plugged in our values. And as you can see, we've already solved for F star B, which is our design value for bending stress. And we have 1684 psi. Now we're also going to solve for E star min. We'll need this value for later.
Step 5.
Solve for Sx. So, using the equation mu equals F star B, which we found earlier, and mu, which we also found earlier, we're going to solve for Sx. So we just rearrange the formula accordingly. Now the equation is Sx equals mu divided by F star B. We're just going to plug and chug, and that answer gives us 47 inches cubed. So, using table B.1 in the back of your book, we're going to size the member. So if you look at the table, you will see the next highest but closest value to 47 inches cubed is 49.91 inches cubed. So scrolling all the way over to the left of the chart, you'll see the nominal size, and that gives us a 4x10 size member. And this is what we will use for the timber beam.
Step 6.
Check stability factor. So, the next step in solving for the stability factor is to solve for LU divided by D. LU was given to us in the problem statement, and it's half the length of the beam. D was given to us, which is our board depth, was given to us by our 4x10 member. So, solving for LU divided by D, we have 7.78 inches. Using page 128, equation 7.10, we see that our value is in between the design values of 7 and 14.3. So our formula for LE, our effective unbraced length, is 1.63 LU plus 3D. That value was given to us is 145.11 inches. Now we'll need to solve for our slenderness ratio. That equation is the square root of LE times D divided by B squared. And this value must be less than or equal to 50. So using the numbers we just solved for, our slenderness ratio is equal to 10. And this is acceptable because it is less than 50. Now we'll need to solve for F-bin. F-bin equals 1.2 times E star min divided by RB squared. We're going to use the E star min that we found earlier in step 4. So FBN equals 8,955.6 psi, and we'll use this value to solve for alpha. So alpha equals FBN divided by F star B, and that equals 5.32 psi. Now we can solve for our stability factor, and that is found in our book, and it's equation 7.5. Helpful hint when solving for stability factor is to go ahead and solve for 1 plus alpha divided by 1.9. Doing this, we found a value of 3.33, which we will go ahead and move into our equation, which ultimately gives us a stability factor of 0.99. So to recap, this is how we designed a timber beam using the special Dr. Rachel Mosier method. Write the problem. Find the load combinations, find the moment, find your design values, solve for Sx, and check your stability factor. So we hope you find this video helpful. This has been a CMT Senior production. I'm Kristen Fields.
I'm Talia Ware.
And I'm Eduardo Aguayo.
Thank you.
Woo!